Thanks. Okay. So we are going to continue with movement in space, motion in space. Second. Okay. So the first thing is that okay. So if we have the position curve, which is our RFT, so here in X, Y, Z, and here's our curve, then our RFT would be a velocity, the RFT would be the curve, this curve, RFT. And then our velocity vector, R prime of t, that would just be the velocity vector. And we can say that that's V of t is equal to R prime of t. And the speed would be the magnitude of R prime of t, like we saw last time. So that would be our velocity vector. And then our acceleration vector is going to be equal to the derivative of our velocity vector, which is going to be equal to the double derivative of the position. So, for example, so here are those definitions. What R prime of t is the acceleration, R of t is the velocity. So now they want us to calculate and plot the velocity and acceleration vectors at t equal 1 for R of t is equal to sine of 2t, negative cosine of 2t. So we have R of t is equal to sine of 2t, negative cosine of 2t, and the square root of t plus 1. So R prime of t, that's going to be 2 cosine of 2t, 2 sine of 2t, and 1 over 2 the square root of t plus 1. So that would R prime, and R prime at 1 would be 2 cosine of 2, 2 sine of 2, and 1 over 2 square root of 2. And this would be our velocity. And then our acceleration would be the derivative of the velocity. So that would be negative 4 sine of 2t, 4 cosine of 2t. And so then this over here is going to be the same as 2 times t plus 1 to the negative 1/2. So the derivative is going to be, 1/2. So the derivative is going to be negative 1 over 4 t plus 1 to the negative 3 over 2. So this is negative 1 over 4 to the t plus 1 times negative 3 over 2. That would be our acceleration vector. And there our acceleration vector at point 1. So a of 1 is going to be negative 4 sine of 2, 4 cosine of 2, and negative 1 over 4 times 2 to the negative 3 over 2. Any questions about this? No? Okay, so the next thing we can do, so we now know how to go from our position, from our RFT to acceleration, but we can go the other way as well. We can go from acceleration to our RFT, so long as we know some initial conditions. So let's just do this example, and it should clarify some of these stuff. So they tell us that A of t is equal to cosine of t, e t, and t. So A of t is equal to cosine of t, e to the t, and t. And then they have that v of 0 is going to be equal, so v of 0 is equal to I, and r of 0 is going to be equal to k. Now let's take the antiderivative of this. So we would get that v of t would be equal, let me actually, okay. So v of t would be equal to to sine of t plus c1 comma e to the t plus c2 comma t squared over 2 plus c3. And v of 0, looking at this over here, looking at that equation that we just wrote out, would be, so you plug in a 0 here, you would get c1 1 plus c2 and c3. But this is also equal to 0, because the v of 0 is equal to I, this is equal to 1, 0, 0, which tells us that c1 is equal to 1. 1 plus c2 is equal to 0, which tells us that c2 is equal to negative 1, and c3 is equal to 0. So let's rewrite our v of t. So now v of t is going to be equal to sine of t plus 1 e to the t plus minus 1 and t squared over 2. Okay, and that's that. Okay, now our r of t, so let's take the antiderivative again. So that would be over here negative cosine of t plus c1. And over here we would get e to the t minus t plus c2. And then over here we would get t to the 3 over 6 plus c3. And we know that r0, so first, what is r0 over here? Let's plug that in. That would be, so over here we would get negative 1 plus c1. And then over here we would get 1 plus c2. And then here we would get c3. And this is equal to k, so that would be equal to 0, 0, 1. Okay. So that would tell us that c1 is equal to 1. And then from here we get c2 is equal to negative 1. And c3 is equal to 1. So now let's rewrite our r of t. So r of t is now going to be equal to negative cosine of t plus 1 e to the t minus t minus 1 and t cubed over 6 plus 1. So
hey, how does C3 equal 1 again?
I
thought it equaled 0, and I wasn't sure if you are doing something different.
No, so sorry, these are different C1, C2s, and C3s. There were ones from over here. I can say that these are the primes, one for R, for the R. So now we need to figure out what they are again. So then you would have this, this, and this. So C3 is equal to 1 because that R of 0 is equal to K. So these were for the V0, C1, C2, and C3. And they come out with constants, and we figure out what those constants are using this over here. And then we figure out what our R of t is. then we figured out what our R of t is by taking the antiderivative, but constants come out of there too. Oh, sorry, this would be prime, prime, and prime.
Okay, that makes sense. Thank you.
So then we get this in the end, and we can plug in any number we want, like, I don't know, 1, and that would get us to what the position is at that time. 2 e to the 1 minus 2 and 1 6 plus 1, and so on. So you might be asked questions like that, or to find the position of a particle at a given time. Okay. So that was this question. So are there any questions about that? Okay, so now they say near the surface of Earth, gravity imparts an acceleration of approximately 9.8 meters per second in the downwards direction. So, which would mean that if we had, well, first, let's just imagine we're standing here, we throw a ball off. It would start, imagine it has no other forces, it would start falling down with an acceleration in the y direction of 9.8 meters per second. Even if it were standing on the floor, it would be there would be a force in the downwards direction, and the force is related to acceleration, and it would be accelerating downwards. So they tell us that, yeah, so the acceleration is this. When a projection in motion occurs with a vertical plane, we can model the motion of the xy using the k. So they're basically saying, okay, let's imagine that we're only in 2 coordinates. And that would mean that our acceleration at this point, our a of t, which we were looking at before, a of t, there won't be a x part, and there would be a negative 9.8 y part. Okay, and they want us to find, and then they say, so now this is the question. A projection is launched from the ground. So let's, so we're standing here, and we launch a projectile, and at an angle, well, that's the angle, at a speed of 100 feet per second. And when we throw this thing at a speed of 100 feet per second, we should remember that there's a y coordinate to this and an x coordinate to this. And we'll have to figure out what that is. Show that the projectile lands at a distance of that from the launching point. Okay, so let's go here. Okay, so again, we're standing here. We shoot the projectile. This is our angle. So that would tell us that the x coordinate over here would be cosine. So 100 times cosine of this angle, and the y coordinate over here would be 100 times sine of the angle. Okay, so that would tell us that at v0, so let's first write down what the acceleration is. So a of t is going to be equal to 0, and I'm going to use their thing, so I'll just go negative 32. This would be in feet. Okay, so that would be our acceleration. And our velocity at time 0, well, we now know what that is because that's this over here. So it would be 100 cosine of the angle, 100 sine of the angle. Okay, now let's find what v of t is. So v of t, that's going to be, so over here we would have C1. So here we'd have C1, a comma, negative 32 t plus C2. And as so let's see what v of 0 is. V of 0 over here would be C1, C2. But that's also equal to this over here, which would be 100 cosine of the angle between these, and 100 of the sine, which tells us that C1 is equal to 100 cosine of this angle, and C2 is equal to 100 sine of this angle. Sorry, 1 second, I need my charger. Okay, let's continue. So that would give us that our V of t, so now we get that our V of t is going to be equal to 100 sine of this angle minus 32t plus 100, oh, 1 second, C1 cosine. So 100 cosine minus 100 sine. Okay. So now our R of t, that's going to be equal to 100 cosine of this angle plus C1 prime. And then over here, we're going to get minus 32t squared over 2 plus 100 sine of t. 1 second. This would be t over here. T plus C2. Now at R0, we would be at 0, 0, because we would be right at this point, at the origin. So, but let's also see what R0 is from this perspective. So we would get, here we would get, oh, sorry, 1 second. Oh yeah, no, it's fine. Yeah, so here we would get C1 prime. Okay, and then in the second component, this is 0, and this is 0, so we would get C2 prime. This is equal to 0, 0, which tells us that C1 prime is equal to 0, and C2 prime is also equal to 0. So now we can write out what our R of t is. So R of t is equal to 100 cosine of this angle times t plus nothing, and negative 32 over 2t squared plus 100 sine times t. Okay. So now they asked us to find where the horizontal, what's the horizontal point where this thing is equal to 0, right? Because basically we launch the projectile here, the vertical component, the y direction is 0, and we launch it, and then it hits here, and the y direction is 0 again. So we have to figure out where this thing is 0 and solve t for that. That's the first thing. So set this to equal to 0. So let's do that. So this would be negative 16 t squared plus 100 sine of the angle times t is equal to 0. But we can assume that t is not equal to 0, because that would be the starting point, and we are not at the starting point, so we can divide by t, so we get negative 16. T is equal to 100, and we can get rid of that, 100 sine of the angle, and divide by 16. So that's what t is going to be. So now if I want to find the place where we land, if I want to find the x coordinate, then I can use this equation over here, plug this for t in there, and I will get that my x coordinate is 100 cosine of this angle times t, which is equal to this, which is equal to 100 sine of this angle over 16. Okay, and that's it. So, any questions about this? Was it clear?
Yeah.
Thanks. One second. Okay. So let's continue. So now we have a, they want us to be able to do this for a circle too. So uniform circular motions. Find the acceleration and the magnitude of the acceleration for the motion of a particle around the circle of radius r with constant speed v. So if we have a circle, we have said before that we can write that r of t is equal to, and over here we have radius r, and then we would have cosine of omega t, some constant, and sine of omega t. These are all the circles we can find, right? So then r prime of t, which is equal to our velocity, okay, here we go. So then r prime of t, which is equal to our velocity, is going to be equal to r, and then we would have over here sine, negative sine, and then omega of omega t, and omega cosine of omega t. That would be our r prime. And then r double prime of t would be equal to big R times omega squared. And this is our acceleration. Okay, times, so negative that times cosine of omega t. And then over here we would get negative omega squared sine omega t. Okay, so this would be our acceleration, and the magnitude of our acceleration, that's going to be equal to r squared, sorry, r from here, and then we would get omega squared from here. This and this would turn, when we do Pythagorean theorem, we take the square root. Well, basically, yeah, it would end up being the square root of this thing squared times cosine omega t squared plus sine omega t squared. And that will be equal to, this is 1, so that would be the square root of r omega squared, which would be r omega squared. And that would be the magnitude of our acceleration. And if you notice, this vector over here pointing at the circle would always be something like that, a vector pointing outwards at the circle. The derivative is going to always be a vector like this, pointing tangent to the circle. The acceleration for the circle has a negative of this component and a negative of this component, so it's going to be pointing inwards. So if you're standing on the circle, you can imagine that the vector is pointing inwards like that. So that's where the acceleration is going to be. Okay. Any questions about that? Okay. So let's continue. So I actually do not want to go too deeply into how to decompose the acceleration vector into two different vectors. It relates back to the projection and all that, and I don't find it that important. So for now, I'm going to skip it. If we ever need it, I'll come back, but I don't think we will. So that would be the end of this section. We have we know what our velocity is, what our acceleration is, what our unit tangent vector is, what our normal vector is from before, and then these stuff, the tangential component of the acceleration and the normal component of the acceleration. For now, we will ignore that. So we're gonna basically stop here for now, and we're gonna have the quiz tomorrow on everything up to curvature. We're not gonna have motion in the quiz. So are there any questions?
For the section about graphs, what exactly are we gonna have to need to know? Like, are we gonna have to graph things on the quiz tomorrow, or just like what equation corresponds to what type of graph?
Yeah, that's basically what you would need to know how to do, and also be able to like trace out some of the functions that these graphs are coming from. So if it's like a hyperbola of two sheets, then be able to explain why there's a missing section in between the two sheets, and where the hyperbolas appear, and stuff like that, where ellipses appear if they do, and things like that. Okay.
Okay, thank you.
How many questions is it again?
There are going to be 5 questions, and it's going to be 3 hours. So you should take it as a review for the test.
Sounds good.
Okay, fine. So any other questions? So we're going to stop here. Again, if we need to go back to finding the tangential component of acceleration, well, it's connected to the dot product. So you should be able to do that by yourself at this point. But to decompose it into the normal part of it. Tangential part, but I would go over that if we need it, but I don't think we're going to need it. So I think we're going to stop here for today. Okay? Okay, have a nice day.